Hello, my name is Tiffany, and I'll be presenting our work on circuit assemblies, a design system for beginners to create 3D printed interactive objects. This pictorial, contributed during my time as a project assistant professor at the University of Tokyo, was largely developed while I was a lead UX designer at Autodesk on Tinkercad, a free web-based tool for prototyping with 3D design and electronics. Using foundational electronic components like LEDs, batteries, and motors, circuit assemblies can be embedded in custom 3D prints that light up, move, and spin. This work is integrated into Tinkercad's 3D modeling environment, an introductory CAD tool where users can move, transform, and group basic shapes together to form more complex designs. Our goal with this work was to consider how we can support young people designing interactive 3D printed things. Prior research has considered alternative processes for generating 3D models through sculpting or crafting enclosures, which eliminates the need for CAD, but also has the additional requirement of using 3D scanners. Others have considered design software for routing electronics directly on the surface of a print, using conductive filaments to build embedded sensors, or encapsulating interactive devices like mobile phones or watches directly into 3D prints. However, the use of specialized hardware or materials, as well as large print sizes and time that may result from incorporating full-size electronic devices, makes these tools less accessible to educational environments that are both budget and time constrained. So in our work, we make several contributions. We interviewed K-12 teachers about how they currently introduce electronics to their students and use insights drawn from these interviews to inform the design of 4 circuit assembly modules. Our pictorial provides a detailed description of the design decisions and features for each of these assemblies, while sharing examples of projects built by students and teachers, as well as reflections on outstanding challenges for supporting beginners integrating electronics into 3D designs. And in this talk, I'll touch upon each of these contributions. Our initial study involved 30-minute semi-structured interviews with 3 educational technology teachers teaching across elementary to high school age youth. These interviews explored how teachers currently introduce electronics and how electronics might intersect with physical and digital fabrication activities, as you see in these photographs here. From these interviews, several insights were distilled. The first is that all teachers spoke of using simple circuits as a base that can be infinitely customized by designing custom enclosures, such as these night lights created by middle school students using the same underlying circuit. Our teacher described this by saying, all the kids make the same circuit, but if they get to customize their own housing around it, it becomes more personally meaningful. Second was the common use of ad hoc materials to try to combat the challenge of securing bulky electronics to custom designs externally. Instead of using soldering irons, materials like hot glue, rubber bands, and tape were often used for temporary rather than robust attachments. Third, teachers specifically sourced age-appropriate parts, choosing components that had large connection points that would be more suitable for the dexterity level of young children. This also helped ensure that electrical connections could be made without the use of soldering irons. And finally, while 2 of the 3 educators spoke of using prototyping toolkits like LittleBits, they also described the power of using basic electronic components, a fraction of the cost at pennies rather than tens of dollars per part. They also enable kids to get their hands on the types of components that professional engineers might use in their own prototyping. These insights led to 3 design goals: to enable users to customize basic behavior through 3D design, use inexpensive electrical components that are age appropriate and would reduce the need for specialized equipment like soldering irons, and finally, to minimize fabrication time and material to make digital fabrication more friendly for classroom environments. Based on these design goals, 4 circuit assembly modules were created. I'm going to walk through one example and then briefly describe the remaining 3. The Move circuit assembly consists of a vibration motor, a switch, and a battery, along with a 3D printed holder. When assembled and powered on, it randomly moves across the surface. This module can then be embedded into custom designs, and depending on the weight of the creation, results in designs that jump or glide. To support users embedding modules into their designs in Tinkercad, we paired each virtual circuit assembly part with a corresponding cutout. A cutout is essentially a negative space, a negative shape that when grouped with a solid produces the hole that's needed to press fit the module inside. So what you see here is a snail that has a cutout grouped with it so that the hole needed to press fit the move module is created at the bottom of the design. So the general steps for using a Tinkercad circuit assembly are to first create a custom design around the circuit assembly cutout in Tinkercad. Then the design is exported and printed along with the circuit assembly holder. The user then assembles the circuit assembly using electrical components and then integrates the module into their design to complete it. Other circuit assembly modules that were developed include Glow, which combines an LED and coin cell battery, Spin, which is used to create designs that rotate continuously using hobby gear motor and a battery box, and Rainbow Glow, the most advanced module consisting of a programmable Arduino Uno and NeoPixel ring to illuminate designs using color LED light sequences. The pictorial describes in detail the design considerations for each of the 4 circuit assemblies and provides links to accompanying tutorials for creating your own designs. In the context of this short presentation, I want to touch upon just 2 considerations that emerged from designing this feature. First, the 3D printed holders used to integrate all electronic components and securely press fit them into people's custom 3D designs provided opportunities to use physical parts as schematics. So for example, on the Glow holder, labels could be used to indicate LED and battery polarity for when people assemble the circuit. And on the Rainbow Glow, there were labels for different pins of the Arduino. And this further provided guidance to users on how to assemble their design. Second, a challenge in creating these modules was balancing ergonomics with part availability. So for example, in order to remove the need for soldering for the move circuit assembly, a very specific type of switch was chosen that has solder lug terminals or pins with holes in them where you could thread the wire through to complete the circuit. This made the design more age appropriate, yet introduced a dependency on a certain physical shape of switch. So working together with SparkFun, we were able to provide a kit of parts to make sourcing easier. By choosing a specific part generally introduces a barrier to how easily users can obtain the needed components to assemble this design. We identified 50 examples of projects created by students and teachers, all shared on social media. These creations begin to show that circuit assemblies were used in a variety of creations, from glowing animals to a walking robot. We did, however, find that the majority of examples were of the Glow circuit assembly, the circuit assembly that consists of an LED and a coin cell battery. Perhaps this is because of the ubiquity of simple LED circuits in introductory maker activities, but it did raise the question of how we can scaffold the experience of incorporating other types of interactivity like motion. I'd like to extend a thanks to the Tinkercad development team and content creators, as well as educators who contributed feedback throughout this process. Circuit assemblies are live on tinkercad.com, so please feel free to try it out yourself and refer to the paper for direct links to supporting tutorials. We hope this work can inspire continued development of prototyping tools that educators and students can engage in learning about integrated product design. Thank you.